Relational algebra. A relational algebra, basically talking about algebra. When we talk specifically about algebra, we are talking about some operators and some operands. Operands could be A and B. Operator can be plus. So when we talk in the context of relational algebra for databases, our operands are relations, and relations are tables. So let's go through some terminologies here. The relational model is based on the mathematical concept of a relation, which is physically represented as a table. The terminology is taken from mathematics, principally set theory and predicate logic. So in the context of relational algebra, relation is the same as table that we are most familiar with. So a relation is a table with columns and rows. Relational database management systems, which we usually refer to them as RDBMS. RDBMS is just simply a set of programs that take care of the relations activities behind the scenes, such as how to save them onto the disk, and simply representing an abstract of our table in a form of table with rows and columns. So some of those databases are MySQL, Oracle, SQL Server, and of course there are some other ones. Another terminology that we need to know is attribute. Then again, I keep repeating, when we talk about these terminologies, we are talking about the terminologies in the context of relational algebra. Attribute is a named column of a relation. Domain. Domain is a set of allowable values for one or more attributes. For example, the domain of attribute 6 means the only acceptable value is M for male and F for female. Another example would be GPA. The GPA is defined as being an integer, and the acceptable values would be between 0 and 4. So that's what the domain is. Tuple is simply a row, and degree is the relationship, is the number of attributes it contains. And this should be relation. So here we simply showing it with the images. The columns are called attributes. The rows are called tuples. The entire attributes and these instances of rows are called relation. And the degree is, of course, the number of attributes. So when we talk about relational algebra, they are divided mainly in two parts. We have unary operators and we have binary operators. The unary operators usually work with one single relation. So one of the operator is this symbol, which is sigma, and the syntax is sigma selection condition and R is the relation. So in this case, it says simply select rows based on that condition from a relation called R. So if this is our relation, then having select where age is equal 50 from S2 relation, which is the relation name, it will give us these two rows. So these are the only two rows that met this condition, age being 50. So what select does, it only gives you a subset of rows or tuples based on that condition. So if the condition is met, then those rows will be the result. And again, the result is itself another relation. So when we talk about relational algebra as far as operands, operands are relation, and they are going to be used as input, but also the output, it would be another relation. Project operation, we use this pi symbol. So in projection, we select the attributes that we want to show. So here we have, say, show the attribute S name and age from S2-1 relation, which is right here. So it is going against this relation, and notice that even though S name and age, they are exactly the same, but it is displayed here only once. So in relational algebra, duplicate rows are eliminated by nature, by its rules. So we can put these two queries together in this way. So the inner query within the parentheses is going to be evaluated first, and then the result will be a relation, and then the outer query, in this case project, is going to go against that relation and then create another relation. All right, if we were to write this statement here in plain query or SQL language that we are accustomed to, it would be select distinct sname age from S2 where age is equal 50. So the reason we are putting distinct keyword here, because in a normal SQL statement that we use, if we don't use the distinct, then we will have, or it will show the result. If there is any duplicate, it will be repeated. By having this, it will mimic exactly like what the relational algebra operators behave. All right, now moving on to binary relational operators. And we have union, intersection, and minus. So we are going to be using these two relations for our examples for these three different operators. Okay, so in this case for the union, it says the union of two relations R and S define a relation that contains all the tuples of R or S or both R and S, duplicate tuples being eliminated, R and S must be union compatible. In other words, if the schema of a two relation match. So basically it says the union compatible in this case means these two tables have to have exact the same number of attributes, and they have to be in the same order, and the attributes have to be union compatible, meaning they have to have the same domain. So something that we mentioned earlier, a domain is a set of allowable values for one or more attributes. So when we say the domain of so and so attribute, that means it calls for its type, data type, and the range of acceptable values. So here we have one example of union. So this is this output, which is another relation, is a result of these two union compatible relations. And when we talk about union, since everything is the same as far as the number and the order of attributes and their domains, we can imagine that we simply append one relation to another relation. And in this case, if there is any duplicate, we simply eliminate it. That's how relational algebra union works. It is true for intersection and minus and everything else, as far as we are talking about relational algebra context. Now we go for intersection. Intersection again must be union compatible. So does minus has to be union compatible. So looking at these two relations, they are of course union compatible. So intersection simply says we are selecting only those rows that are shared between these two union compatible relations. So here we have a SID 40 and 30, and here we have 30 and 40 in both tables or relations. The minus, we can have S1 minus S2 or S2 minus S1. So these two are different. The result, which is another relation, would be different. So what it means here, S1 minus S2 says we are going to display the rows not including anything from S2 and also not including any row that exists in S2. So 40 and 30 does exist in S2, so we don't want them. The only row that is left is this row, and that's the result. The same is true if we do, say, S2 minus S1. We say we want everything that is in S2 except the ones that match in S1. So again, the SID 40 and 30, they both exist in here. So we don't include them, and of course we don't include anything from S1. So therefore, these two subtraction, or minus I should say, are different. Now we move on to Cartesian product. In Cartesian product, they don't have to be union compatible, and that's why we have two relations that have different number of columns. And if we implement the product, you will see here in this area we have these rows from this table with one of the rows in the other table. So 10, 80, which is from this, and also all the rows from here. Then again 4, 7 from this relation with all the records from the other table. So we are simply putting both of these tables together, and the resultant number of rows is always equal to the number of rows in one relation multiplied by the number of rows in another relation. And in this case we have 12 rows. Alright, next we are going to be talking about join. This is the symbol used for join. And of course, join is one of those operations very important to relational database, that we will join tables together in order to retrieve the requested data. So here again I'm using two different relations. They don't have to be union compatible, so they have different number of rows and or columns, and they have different domain in this case. So the syntax for join is, they have a relation R to the left side of it, then on the right side we have the condition and another relation. So in this case we go against S1 and S2 relations, and we want to join these two relations based on this condition. So if this condition is met, then we join the attributes of one relation to the other relation. And in this case, this is the result. So the only rows that match in both of these relations are the one with the ID of 40 and 30. So here's the note, says the difference between Cartesian or product and join is that we use condition in join and therefore display only the rows from two relations that match the condition. Alright, so there are two variations of join: equivalent join and natural join. So again we go against these two relations, and we already saw this, so here we go over it again. We have a S1 that we are going to join with S2 based on this condition. So here is one table, S1, and here's the S2 table, and there are only two rows that matched and are displayed there. We also have natural join. And natural join basically has no condition. The condition is implied. So as long as two relations that we are going to join have the exact same name for an attribute with the same domain, then we don't have to specify the condition. So in our case, we have SID here and SID here. And when we use natural join, the extra or duplicate column is eliminated. So let's look at the differences between the two. So in equijoin, we use this symbol. In natural, we use this star or asterisk. In equijoin, the relation will have two occurrences for the join attribute SID, as I just described. The relation will have one occurrence for the join attribute SID in natural join. So in equijoin, we use the equal sign, as we saw in here, in order to evaluate the condition that is met between the two relations. In natural join, we do not use, but we should know that the name has to be also the same in two relations in order for this to work. All right? Now let's go over the flavor of the inner join and outer join. The inner join, what it means, it is only interested in the rows that are met based on that condition between two relations. But in outer join, we can expand those selection depending whether we select the left or right relations. So let's go over these with the examples in this case. All right, so these are the symbols of join by having these extra tick marks to either side. So if it is pointing to the left, that means it is outer left join. If it is to the right, it is outer right join. And if it is in both sides, that means it is a full outer join. So the left basically says, and by the way, we are looking at these two relations. So these are the result of from these two relations as input based on the choices that we have chosen here. So in this case, it says, I want to include the rows that match in both relations, but also I want to maintain the other rows on the left side. So in this case, this row already exists in R, but since there is no value or not found in the other relation, we have to put null in these three columns. So when we talk about outer left join, it is exactly the same as left, but we do it the opposite way. So we do need all of these rows that exist in S in this case, because it is the right one, the right side one. And we include those that match in our relation. So we have a 40 and 30 that match. Here's a 40 and 30 SID that match in here. But the ones that don't match, don't exist in relation R, we simply put null. And here it is a full outer join, and of course it will be including both of these. So the rows that are on the left will be included. We have three, or all three of them are here, and also the ones that don't have values, don't exist on the right side, we simply put null. And the same is true when we look at the S table. We put all the rows, and the ones that are not found on the left side as far as being matched, then we put null. So we can summarize the inner join and the outer join in this diagram, in this Venn diagram. So when we talk about inner join, we are only interested in the intersection here. And when we are talking about outer join, we have these three different flavors. So the left outer join includes not only the intersection that they have, but also everything else in R. For the right outer join, again, we are not only interested in the intersection, but also everything on the right. And of course, when we talk about the full outer join, it includes all of these. All right?